You are listening to MongoDB for Developers, a practical guide to NoSQL database design and development. Like and subscribe to keep up to date on our latest audiobooks. MongoDB for Developers, a practical guide to NoSQL database design and development. Chapter 1, Understanding NoSQL and MongoDB's place in the ecosystem. In the beginning of the digital age, data was often uniform, structured, and fit perfectly into the rows and columns of relational databases. These systems, based on SQL, represented a highly organized library, where every book had its fixed shelf and catalog entry. But as the internet swelled, bringing with it a tide of new applications, diverse data types, and an insatiable demand for instant access on a global scale, the limitations of this highly structured approach became apparent. Imagine trying to categorize every single piece of information on the internet, from a tweet to a sensor reading, a user profile to a video transcript, into a rigid spreadsheet. It becomes cumbersome, inefficient, and sometimes nearly impossible. Relational databases, while excellent for many scenarios, found themselves challenged by the sheer volume, velocity, and variety of modern data. Their rigid schemas made it difficult to adapt quickly to changing business requirements, and scaling them horizontally to distribute data across many servers could be complex and costly. This led to a significant impedance mismatch for developers, where the flexible objects in their programming languages had to be painstakingly mapped to a rigid relational schema. Moreover, an increasing amount of data was unstructured or semi-structured, like JSON, XML, or logs, which didn't fit neatly into predefined tables. Out of this landscape emerged a new category of databases known as NoSQL, often interpreted as not only SQL. This wasn't about replacing relational databases entirely, but about expanding the toolkit. The idea was to embrace polyglot persistence, using the right database for the right job, rather than forcing all data into a single model. This paradigm shift recognized that different types of data and different application needs benefit from different storage and retrieval approaches. The NoSQL movement blossomed into several distinct categories, each designed to excel at specific data challenges. First, we have key-value stores. Think of these as incredibly efficient, giant hash maps or dictionaries. You give it a unique key, and it gives you back a value. They are incredibly fast for simple reads and writes, making them ideal for caching, session management, or storing game leaderboards. Examples include Redis and Amazon DynamoDB. Next, and central to this book, are document databases. Imagine a modern digital archive or a filing cabinet where each file is a self-contained document. Unlike the rigid rows of a relational table, each document can be unique, holding various kinds of information, even if it doesn't quite match all the other files in that collection. This flexibility makes them perfect for content management, user profiles, product catalogs, and any application where data structures might evolve rapidly. MongoDB and Couchbase are prime examples. To illustrate, imagine a world where data isn't neatly organized in a spreadsheet, but is more like a collection of unique business cards or resumes. Each one might have different fields, but you can still search and organize them effectively. That's the spirit of NoSQL's document model. Then there are column family stores, sometimes called wide column stores. These are optimized for handling very large datasets that are often sparse, meaning many rows might not have values for all columns. They excel at analytical workloads and storing time series data. Apache Cassandra and HBase are prominent in this category. To illustrate, picture a very wide table, where columns can vary greatly from row to row, optimized for performance across massive distributed systems. Finally, we have graph databases. If your data is highly interconnected, like social networks, recommendation engines, or fraud detection systems, graph databases are your go-to. They store data as nodes and edges, making it incredibly efficient to traverse relationships. Neo4j and ArrangoDB are popular choices here. Conceptually, think of a physical network of interconnected points, where you can quickly jump from one point to another following the connections. Among these diverse NoSQL options, MongoDB has emerged as one of the most widely adopted and versatile. Its success lies in several key strengths that resonate deeply with developers. Its biggest strength is the document model itself. Since it directly maps to the objects and structures developers work with in modern programming languages like JavaScript, Python, or Java, it feels intuitive. This significantly reduces the impedance mismatch developers often face with relational databases, making development faster and more natural. This model also provides unparalleled flexibility. MongoDB's schema is dynamic. You don't need to define the structure of your data upfront. You can add new fields to documents or change existing ones without performing complex database migrations. This is a game changer for agile development, allowing applications to evolve rapidly. Scalability is another cornerstone. MongoDB was designed from the ground up for horizontal scaling, meaning it can distribute data across many servers to handle increasing workloads. It offers built-in features for both replication, ensuring high availability and data redundancy, and sharding, which partitions data across a cluster of machines. We'll delve deeply into both of these concepts later in the book. Despite its flexibility, MongoDB provides a rich query language. You can perform complex queries, filter, sort, and even use regular expressions to find exactly the data you need. The Aggregation Framework, a powerful feature we'll dedicate an entire chapter to, allows for complex data transformations, analytics, and reporting right within the database, much like an advanced data pipeline. Finally, MongoDB boasts excellent performance for many common application patterns, an extensive ecosystem of tools, drivers for almost every major programming language, and a large, vibrant community that contributes to its continuous improvement. However, it's also important to understand when MongoDB might not be the best fit. If your application relies heavily on complex, multi-document ACID transactions that absolutely must ensure data consistency across many different pieces of information that update simultaneously, a traditional relational database might still be a more robust choice. Though MongoDB has made significant strides in transactional capabilities recently. Similarly, for data that is inherently and rigidly relational, like complex financial ledgers with many interdependencies, an RDBMS might prove simpler to manage. To really understand MongoDB, let's break down its fundamental building blocks. These are the equivalent of tables and rows in the relational world, but with an important twist. The most basic unit of data in MongoDB is called a document. Think of a document as a single record, essentially a JSON-like structure comprised of field value pairs. Each document can have nested documents or arrays, making it incredibly expressive. For example, a customer document might contain their name, email, and then an embedded address document with street, city, and zip code fields. It could also have an array of recent orders, each order being another embedded document. In essence, a MongoDB document is like a single object in your programming language, serialized for storage. A collection is a group of documents. This is similar to a table in a relational database, but with a crucial difference. Documents within a single collection do not need to share the same structure or schema. While best practices often suggest maintaining a consistent structure for easier querying, MongoDB does not enforce it. This schema flexibility is one of MongoDB's most powerful features. A database is a physical container for collections. Just like in the relational world, you can have multiple databases on a single MongoDB server, each containing its own set of collections. For example, you might have one database for your primary application data, another for analytics logs, and a third for user management. Finally, let's talk about BSON. When you interact with MongoDB, you'll typically be working with data that looks and feels like JSON or JavaScript object notation. However, internally, MongoDB stores this data in a binary encoded serialization format called BSON, which stands for binary JSON. Why not just use plain JSON? BSON is more efficient for several reasons. It supports more data types than standard JSON, including things like dates, a special unique identifier type called object ID, and binary data, which are crucial for real-world applications. It's also faster for MongoDB to serialize and deserialize, leading to better performance. So, while you'll see and use JSON-like objects in your interactions, remember that behind the scenes, MongoDB is optimizing your data with BSON. Think of BSON as JSON's more efficient, binary cousin, designed for speed and richer data handling within MongoDB itself, while you'll typically interact with it using standard JSON syntax. To consolidate, let's outline common scenarios where MongoDB shines and when it might be less ideal. MongoDB is an excellent choice for content management systems and catalogs, where products, articles, or other content items have varied attributes and evolve frequently. User profiles and personalization, storing flexible user data, preferences, and activity feeds. Real-time analytics and IoT data, handling high volumes of rapidly arriving, often semi-structured, data streams. Mobile applications, where data needs to be easily synchronized and can handle occasional offline states. Applications with evolving data requirements. If your application, and thus your data schema, is expected to change frequently, MongoDB's flexible schema minimizes the overhead of database migrations. Microservices architectures, where each service might manage its own data and benefit from a database suited to its specific needs. Conversely, MongoDB is less suited for highly complex, multi-entity ACID transactions. While MongoDB now supports multi-document transactions for applications fundamentally defined by complex, interlocking transactional integrity across many different data entities. A traditional RDBMS often provides a simpler model, strictly relational data with infrequent changes. If your data is inherently tabular, highly normalized, and rarely changes its structure, the overhead of a document model might not provide a significant advantage over a relational database. Purely archival large binary files. While MongoDB can store binary data, for very large files, like high-resolution images or videos, dedicated object storage solutions like Amazon S3 or Google Cloud Storage are typically more cost-effective and performant. By understanding these distinctions and MongoDB's core components, you're now equipped to appreciate why and how it became such a pivotal tool for modern software development. In the next chapter, we'll dive right into getting MongoDB installed and connected so you can begin practical interaction with these concepts. Chapter 2, Getting Started. Installation, setup, and basic concepts. Now that we understand the why of MongoDB and its place in the modern data landscape, it's time to roll up our sleeves and explore the how. In this chapter, we'll move from theory to practice, guiding you through the essential steps of setting up a MongoDB environment and making your first connection. This will lay the groundwork for all the practical examples and deep dives that follow. Your first decision will be choosing where to run your MongoDB instance. You have 3 primary choices, each with its own advantages. A local installation on your own machine, using MongoDB Atlas in the cloud, or running MongoDB within a Docker container. For learning and development, a local installation on your own computer is often the most straightforward. It gives you full control and doesn't require an internet connection once set up. If you're on Windows, macOS, or Linux, MongoDB provides specific installation packages and instructions. The general process involves downloading the MongoDB server package and then running an installer or using your system's package manager. For instance, on Linux, you might use apt or yum, while on macOS, Homebrew is often a popular choice. The exact commands vary by operating system, but the detailed, up-to-date instructions are always available on the official MongoDB website. You'll also need to consider where MongoDB will store its data files and ensure it has the necessary permissions to write to that location. Once installed, starting the MongoDB server typically involves running a command like mongode from your terminal or ensuring a background service is active. A highly recommended option, especially for those who prefer to avoid local setup complexities or want a production-ready cloud environment, is MongoDB Atlas. This is the official MongoDB cloud service, and it's a fully managed database as a service. With Atlas, MongoDB handles all the infrastructure, patching, backups, and scaling for you. It offers a generous free tier, often called the M0 free tier, which is perfect for learning, prototyping, and small applications. To get started with Atlas, you'll visit their website, sign up for an account, and then proceed to provision a cluster. A cluster is a set of MongoDB servers that work together. You'll choose your preferred cloud provider, like Amazon Web Services, AWS, Google Cloud Platform, GCP, or Microsoft Azure. Select a region closest to you and pick your cluster size. Atlas simplifies the process significantly. You get a connection string, and MongoDB handles the underlying infrastructure. Finally, for developers who appreciate isolated environments and portability, running MongoDB in a Docker container is an excellent choice. Docker allows you to run applications within lightweight, self-contained packages called containers. Think of it as a virtual machine purpose-built just for that one application, making it easy to start and stop, and ensuring consistent environments across different machines. With Docker, you typically pull a MongoDB image, that's a pre-built template, and run it as a container with a single command. You can easily map ports to access the database from your host machine and mount volumes to ensure your data persists even after the container is stopped. For example, a simple command might look like docker run name mymongo p27017 27017dmongo, which starts a MongoDB server in a container named mymongo, making it accessible on port 27017 of your host machine, and running it in the background. Once your MongoDB instance is up and running, you'll need a way to interact with it. The two most common methods are the Mongo shell and MongoDB Compass. The Mongo shell is MongoDB's command line interface. It's an interactive JavaScript client that allows you to directly execute commands against your MongoDB instance. If you installed MongoDB locally, you'll open your terminal or command prompt and simply type mongosh for the newer shell, which is recommended, or Mongo for the legacy shell. This will connect you to your local MongoDB server. If you're using MongoDB Atlas, you'll typically be provided with a connection string that you'll use along with the mongosh command. Once connected, you'll see a prompt where you can start typing commands. For example, show DBS will list all the databases on your server, and use myApplicationDB will switch to or create a database named myApplicationDB. You can then type show collections to see the collections within that database. When you open your terminal and type mongosh, you'll see a prompt appear, signaling that you're now connected to your MongoDB server, ready to issue commands. It's like stepping into the control room of your database. For a more visual and intuitive experience, or if you prefer a graphical user interface, MongoDB Compass is an excellent tool. Compass is a free, official GUI that provides a powerful way to interact with your data. It allows you to visually explore your schema, run ad hoc queries, interact with your data, and even provides performance metrics. To connect using Compass, you'll launch the application and provide a connection string, a URL-like address that tells Compass where your database is located, along with any necessary authentication credentials. Once connected, you'll see a clear visual representation of your databases, collections, and sampled documents, making it easy to browse and query. Now that you're connected, let's learn how to create your very first database and collection. Unlike traditional relational databases, where you might explicitly run create database and create table statements, MongoDB has a more fluid approach. If you try to switch to a database name that doesn't yet exist, for example, by typing use my first database in the mongosh shell, MongoDB doesn't immediately create it. The database is only truly created the moment you insert your first document into one of its collections. Similarly, you don't explicitly create a collection beforehand. You simply start interacting with it. For instance, if you're in the My First database and you type db.users.insert1, name, Alice, age, 30, MongoDB will then create the user's collection if it doesn't already exist within My First database, and then insert that document. This create-on-demand behavior greatly speeds up iterative development, allowing you to rapidly prototype and iterate on your data models. At the heart of all database interaction lies an acronym you'll hear frequently, CRUD. This stands for Create, Read, Update, and Delete. These are the 4 fundamental operations you'll perform with any database, and MongoDB provides powerful yet straightforward methods for each. Create C. This operation involves adding new data to your database. In MongoDB, this means inserting new documents into a collection. You'll use methods like insert1 to add a single document or insert many, to add multiple documents at once. Read R, this is about retrieving data from your database. The primary method for this is find, which allows you to query collections based on various criteria. You can specify conditions to filter documents, project-specific fields, and sort the results. Update U, this operation involves modifying existing data. You'll use methods such as update1 to update a single document that matches your criteria, update many, to update multiple documents, or replace one, to completely replace a document. MongoDB also provides powerful update operators to make specific changes to fields within a document Arabic ba, Arabic dal, Arabic wow, Arabic noon affecting other fields. Delete D. Finally, this operation is about removing data from your database. You'll primarily use delete1 to remove a single document or delete many, to remove all documents matching a specified filter. You can also drop entire collections or even databases if you want to remove all their contents. These CRUD operations form the bedrock of all database interaction. In the following chapter, we will delve into each of these operations in much greater detail, providing practical examples and demonstrating how to wield them effectively to manage your data within MongoDB. By the end of the next chapter, you'll be performing sophisticated data manipulations, retrieving exactly what you need, and confidently managing your MongoDB collections. Chapter 3. Mastering CRUD Operations. The core of data interaction. In the previous chapter, we covered the fundamental concept of CRUD operations: create, read, update, and delete. These 4 pillars govern all interactions with your database. In this chapter, we'll dive deep into each one, exploring the syntax, options, and practical considerations for effectively manipulating data within MongoDB. Understanding these operations thoroughly is crucial, as they form the foundation for building any application on top of MongoDB. Let's begin with creating data. This is how you populate your MongoDB collections. The simplest way to add a single document to a collection is using the insert1 method. For example, if you wanted to add details about a new customer to a collection named customers, you would typically type something like db.customers.insert1. Name: Alice Smith, email, alice@example.com, is active. True. After executing this, MongoDB inserts the document and returns a confirmation that includes the unique identifier for the newly inserted document. Every document in MongoDB must have a unique id field. If you don't explicitly provide one when inserting a document, MongoDB automatically generates an id for you. This auto-generated id is an object ID data type, a special 12-byte identifier that is unique across machines and time, making it excellent for distributed systems. It's designed to be monotonically increasing, meaning that newly generated object IDs are generally larger than previous ones, which is useful for insertion order and performance. This id field is crucial because it serves as the primary key for your documents, allowing for fast and efficient retrieval. What if you need to add multiple documents at once? That's where insert many comes in. Instead of a single document, insert many takes an array of documents. For example, to add several new products to a products collection, you might use db.products.insertMany, name, laptop pro price, 1200 category, electronics, name, wireless mouse price 25 category, accessories, name, external SSD price 150 category, storage. This is usually more performant than performing multiple insert1 calls individually, as it reduces network overhead. Now that we have data in our collections, let's explore reading data. This is arguably the most frequent operation you'll perform, as applications constantly need to retrieve information. The primary method for querying documents is find. When used without any arguments, find retrieves all documents within a collection. This is rarely what you want in a real application. Typically, you provide a query filter document as the first argument to find, to specify which documents you want to retrieve. The filter document uses field value pairs to match documents. For instance, db_customers_find is active. True would return all documents in the customer's collection where the isActive field is set to true. The second optional argument to find is a projection document which specifies which fields to include or exclude from the result. For example, DB customers find name 1 email 1 id. 0 would return only the name and email fields for every customer, explicitly excluding the default id field, which is included by default unless you tell MongoDB not to. The 1 means include the field, and 0 means exclude it. Matching on exact values is straightforward, but often you need more sophisticated criteria. MongoDB offers a rich set of query operators. These are special operators that begin with a $sign and allow you to build complex queries. Comparison operators, these are used for comparing values. Ek equal to db.productsFind, price. Ek 150. Ni not equal to db.productsFind, price. Ni 150. GT greater than db.productsFind, price. GT 100. GTE greater than or equal to db.productsFind, price. GTE 100. LT less than db.productsFind, price. LT 100. LTE less than or equal to db.productsFind, price. LTE 100. In value is in an array, db.productsFind category. In electronics, storage, nin value is not in an array, db.productsFind category. Nin electronics, storage. Logical operators combine multiple query expressions, and db.productsFind and price, GT 100 a category, electronics, or db.productsFind or price, LT 50 category, accessories, not to, negates a query expression. Nor joins query clauses with a logical nor. Element operators query based on the existence or type of a field. Exists, DB customers find, email. Exists. True finds documents where email field exists. Type, db.productsFind, price. Type, double, finds documents where price field is of type double. Array operators. Query documents based on array fields. All, matches documents where the array field contains all the specified elements. Size, matches documents where the array field has a specific number of elements. Match, matches documents that contain an array field with at least one element that matches all the specified query criteria. This is particularly useful for querying arrays of embedded documents. For instance, DB orders find items. match, producted, P123, quantity. GTE 5, it would find orders that include an item with a specific product ID and a quantity of 5 or more. Querying embedded documents and arrays is a common task. To query fields within an embedded document, you use dot notation. For instance, if a customer document has an embedded address subdocument with a city field, you would query like this. DB customers find address city, New York. For arrays, you can query for specific elements within the array, as shown with match above. Moving on to updating data. As your application evolves, the data it manages will change. MongoDB provides powerful methods for modifying existing documents. Update 1. This method updates a single document that matches your filter criteria. It takes 2 primary arguments: a filter document to identify the target document, and an update document that specifies the changes to be made. Update many. Similar to update 1, but it updates all documents that match the filter criteria. Replace 1. This method completely replaces a single document that matches the filter. Be cautious with replace 1, as it will overwrite the entire document, except for its id. Any fields not specified in the replacement document will be removed from the original document. When you're updating documents, you'll primarily use update operators. These prefixed operators tell MongoDB how to modify specific fields within a document rather than replacing the entire document. Set sets the value of a field. If the field doesn't exist, set adds it. DB customers update 1, name, Alice Smith, set, email, alices@example.com, phone, 5:55 to 12:34, unset, removes a specified field from a document. DB customers update 1, name, Alice Smith, unset, phone. Note that the value provided to unset doesn't matter, an empty string is commonly used. Increments the value of a field by a specified amount. Useful for counters. db.products, update 1, name. Laptop Pro, Inc., stock. Push adds an element to an array. If the field is not an array, it converts it to an array. db.users, update 1, username. Bobby push, hobbies, gardening. Pop removes the first -1 or last 1 element from an array. db.users, update 1, username. Bobby pop, hobbies 1 removes last. Add to set. Adds an element to an array only if it doesn't already exist in the array. Prevents duplicates. db.users, update 1, username. Carol, add to set. Skills, MongoDB. Finally, we have deleting data. This allows you to remove documents, collections, or even entire databases. Delete 1 removes at most one document that matches the specified filter. db.customers.delete1 is active. False, delete many. Removes all documents that match the specified filter. If you pass an empty filter document to delete many, it will delete all documents in the collection, so use this with extreme caution. db.customers.deletemany, status, inactive, drop. This is a more drastic measure. dbMyCollection drop. This command permanently removes an entire collection from the database, including all its documents and indexes. There is no undo. db-drop database. This command completely removes the currently selected database. Again, there is no undo, so be very careful when using this in development or production environments. Let's consider some hands-on examples to solidify these concepts and highlight common pitfalls. Example 1, managing an inventory. Imagine an inventory collection where each document represents a product. Create. Add a new product. db.inventory.insert1, item, charger, QTY50 tags, electronics, mobile, size, H10W5 cm. Read, find products with quantity less than 20. db.inventory-find, QTY, LT20, find charger in electronics category. db.inventory-find, item, charger, tags, electronics, update. Reduce the quantity of a specific item after a sale. db.inventory-update1, item, charger, Inc., QTY-5, add a new tag to the laptop. db.inventory-update1, item, laptop Pro, push, tags, discount, change dimensions. db.inventory-update1, item, charger, set, size H12, delete, remove products that are out of stock. db.inventory.deletemany, QTY, 0, common pitfalls. Forgetting to use query operators. A common mistake is trying to query for ranges or existence without the $prefixed operators. For example, db.productsFind, price, 100 won't work. You must use price. GT, 100, not understanding update 1 versus update many. Accidentally using update 1 when you intend to modify multiple documents, or worse, using update many without a specific filter, leading to unintended mass updates. Accidentally overwriting with set v's. Other operators. If you use set on a complex subdocument, it will replace the entire subdocument. If you only want to change a nested field, use dot notation. For instance, set address, city, New York would replace the entire address document, whereas set address city, New York would only update the city field with an address. Misusing drop. Many developers, especially beginners, mistakenly use db.collectionDrop or db-drop database without backups, leading to irreversible data loss. Always double-check before executing these commands in critical environments. Mastering these CRUD operations is fundamental to becoming proficient with MongoDB. They are the tools you'll use day in and day out to interact with your data. In the next chapter, we'll build upon this foundation by exploring more advanced querying techniques that allow you to retrieve and manipulate your data with even greater precision and efficiency. Chapter 4, Advanced Queries and Data Retrieval. In the previous chapter, we established the fundamental CRUD operations, focusing on the basics of creating, reading, updating, and deleting data. While Find is your primary tool for retrieving documents, MongoDB offers a rich set of additional methods and operators to fine-tune your queries, control the output, and gain deeper insights from your data. This chapter delves into these advanced techniques, allowing you to craft highly specific and efficient data retrieval operations. Let's begin with ordering our results. When you perform a find operation, the order of documents returned is not guaranteed unless you explicitly specify it. This is where the sort method comes in. Sort takes a document specifying the fields to sort by and their order. A value of 1 indicates ascending order and -1 indicates descending order. For instance, db.productsFind sort price 1 would return all products sorted by price from low to high. To sort by price descending, then by name ascending for products with the same price, you would use db.productsFind sort price -1 name 1. Think of this as organizing a list of items. You first sort by one criterion, and then for items that are similar under that first criterion, you apply a secondary sort. For pagination and controlling the number of results, limit and skip are indispensable. The limit method restricts the number of documents returned by a query. For example, db.usersFind limit 10 would return only the first 10 users found. The skip method, on the other hand, bypasses a specified number of documents. Combining skip and limit is the standard approach for implementing pagination. To get the second page of 10 users, i.e., users 11 to 20, you would use db.usersFind skip 10, limit 10. Conceptually, it's like scrolling through search results. Skip takes you past a certain number of initial results, and limit determines how many items are shown on the current page. However, be aware that for very large offsets, skip can become inefficient on large datasets, as the database still has to read and discard the skipped documents. Sometimes you don't need the actual documents, but just a count of how many match your criteria. Count documents is the method for this. For example, db.orders.countDocuments status pending would return the total number of orders with a pending status. If you just need a quick, possibly approximate, count of all documents in a collection without any filter, estimated document count can be faster as it uses metadata rather than scanning the collection. To find unique values for a specific field across documents in a collection, you use the distinct method. For instance, db.productsDistinct category would return an array of all unique categories present in your products collection, like electronics, books, clothing, and so on. This is very useful for populating drop-down menus or analyzing categorical data. Beyond exact matches, you often need more flexible search capabilities. Regular expressions can be used directly within your queries for pattern matching. For example, to find all customers whose name starts with Joe, you could use db.customersFind name /Joe/. For case-insensitive searches, you might add options db.customersFind name John I. While powerful, regular expression queries can be resource-intensive, especially if not anchored to the beginning of a string, as they may require full collection scans without appropriate indexing. For more efficient and scalable full-text searching, MongoDB offers built-in text search. To use it, you first need to create a text index on the fields you want to search. For example, db.productsCreateIndex. Description, text. Once indexed, you can perform queries using the text operator and search value, db.productsFind, text, search. Wireless mouse. This will find documents where the description field contains the words wireless or mouse. Text search can also rank results by relevance using the meta text score projection. Think of it like a miniature search engine built directly within your database, optimized for finding keywords within large blocks of text. MongoDB also excels at handling spatial data through geospatial queries. If your documents contain geographical coordinates, you can enable geospatial indexing and perform sophisticated location-based queries. For example, to find all restaurants within a certain radius of a specific point, you might use GeoWithin with a centersphere operator. db.restaurants_find location, GeoWithin, centersphere, -74.0060, 40.7128, 103963.2. This example finds restaurants within 10 miles of New York City, where -74.0060, 40.7128 are longitude and latitude, and 3963.2 is the approximate radius of the Earth in miles. Other operators allow you to find points within a box, or points that intersect with a given polygon, geometry with polygon. This is incredibly powerful for location-aware applications, like ride-sharing services, delivery apps, or local business finders. To truly understand how MongoDB is processing your queries and to identify potential performance bottlenecks, the explain method is your best friend. When you append explain to a query, instead of returning the query results, MongoDB provides a detailed query plan. This plan tells you exactly how MongoDB intends to execute your query, which indexes it will use, or if it will perform a collection scan, the order of operations, and how many documents it had to examine. For example, db.productsFind, category, electronics, explain execution stats would provide verbose statistics, including execution time and number of documents returned versus scanned. Interpreting the explain output is a critical skill for performance optimization. It reveals whether your queries are performing efficiently or if they are needlessly scanning large portions of your database. By combining these advanced query methods and understanding their nuances, you can retrieve precisely the data you need from your MongoDB collections, whether you're paginating results, finding unique values, performing text searches, or even locating data on a map. These tools provide the precision and power necessary for building complex, data-driven applications. In the next chapter, we'll shift our focus from retrieving data to designing how that data should be stored for optimal flexibility and performance, exploring the critical topic of schema design in the NoSQL world. Chapter 5, Schema Design, the NoSQL Way of Thinking. Up to this point, we've focused on interacting with MongoDB, but a crucial element for building high-performance, scalable applications is how you structure your data. In typical relational databases, schema design involves meticulous planning of tables, columns, relationships, and normalization upfront. MongoDB, being a NoSQL document database, approaches schema design with a different philosophy, often embodying the phrase schema on read, which is a distinct departure from the schema on write of relational systems. The most significant advantage of MongoDB for developers is its flexible schema. This means that documents within a single collection do not need to have the same fields, structure, or even data types for common fields. This inherent flexibility provides immense agility. Imagine you're building an e-commerce platform. Some products might have a color field, others a size, and some might have both or neither. In a relational database, you'd need many nullable columns or separate tables. In MongoDB, each product document can simply store the attributes relevant to it. This makes it incredibly easy to evolve your application's data model without costly and complex database migrations. When a new product attribute is introduced, you simply start adding it to new documents. Existing documents remain unaffected. However, flexible doesn't mean schemaless. While MongoDB doesn't impose a rigorous schema, you, as the developer, still need to think carefully about your data structure. A well-designed schema leads to efficient queries and optimal performance, while a poor one can lead to headaches. This is where the schema on read comes in. You define your schema as your application reads the data, and your application code needs to be resilient to varying document structures. Optionally, MongoDB does offer schema validation, which allows you to enforce certain rules on your document structure if needed, providing a middle ground between complete flexibility and strictness. For example, you can ensure that a price field always exists and is a number, without mandating every possible field in a document. One of the most critical decisions in MongoDB schema design revolves around embedding versus referencing. This is akin to choosing between joining tables or denormalizing data in a relational context, but with a different set of considerations and trade-offs. Embedding means storing related pieces of data within a single document. For example, if a customer document stores a name and email, its address might be an embedded subdocument. Name: Alice Smith, email: alice@example.com, address. Street: 123 Main Cent, city, Anytown. The advantages of embedding are significant. Performance: all related data for a single entity is stored together, eliminating the need for joins or multiple database lookups. This significantly reduces the number of read operations, leading to faster data retrieval. Atomicity: updates to embedded documents happen atomically, meaning the entire update either succeeds or fails, ensuring data consistency for that embedded block. Simplicity, retrieving the complete object, like a customer with their address, is a single query. However, embedding also has potential downsides. Document size limits. MongoDB documents have a maximum size limit of 16 megabytes. While 16 MB is substantial, for extremely large arrays or deeply nested structures, this can become a concern. Data duplication. If the same embedded piece of data needs to appear in multiple documents, e.g., a product embedded in many order documents, updating that common embedded data requires updating it in every document where it's replicated. This leads to denormalization and data duplication, which can improve read performance at the cost of more complex write operations and potentially stale data if updates are not handled carefully. Querying embedded data. While possible, querying and indexing deeply nested or very large embedded arrays can sometimes be less efficient than querying top-level fields. Referencing means storing relationships between data by including a reference, like an id, to another document in a separate collection. For example, a customer document might store the ids of order documents in an array. Name: Bob Johnson, orders. Object ID: 60C72B2F6B3E7A00-1A to B3C4D. Object ID: 60C72B2F6B3E7A00-1A to B3C4E. The actual order details would reside in a separate orders collection. When to use which? This is a crucial design decision. The general rule of thumb is, embed data if it's frequently accessed together, has a one-to-one or one-to-few relationship, and doesn't grow unbounded. Think of has-a-type relationships where the embedded data is strongly tied to the parent document. For example, a credit card linked to a user or an address for a person. Reference data if it's accessed less frequently with the parent, has a one-to-many or many-to-many relationship, is large or grows unbounded, or needs to be queried independently. For example, customer to orders, many orders per customer, or products to categories, many products in one category, one product in multiple categories. Let's illustrate with common relationship types. One-to-one. Ideal for embedding. For example, user profile details like preferences could be embedded within the main user document. One-to-many, embedding small fixed number. If the many side is relatively small and doesn't grow endlessly, e.g., a person having a few credit cards, you can embed them in an array. Referencing large growing. If the many side can be very large, e.g., a customer having thousands of orders or a blog post having hundreds of comments, referencing is usually better. Here, you might store an array of ids in the one side document or store a reference to the one side's id in the many side documents. For instance, each comment document could have a post-id referencing the post it belongs to. Many-to-many, always use referencing. For example, students and courses. A student enrolls in many courses, and a course has many students. You would have a students collection and a courses collection, and each document would contain an array of ids referencing the related documents in the other collection. Modeling tree structures and more complex relationships. MongoDB also provides patterns for hierarchical data. For example, a comments collection might use parent id references to build a threaded discussion, or an ancestors array to efficiently query subtrees. While these can be more complex to manage, MongoDB is flexible enough to accommodate various data models. Denormalization and data duplication. Balancing reads and writes. In the relational world, normalization, reducing data redundancy, is key. In MongoDB, denormalization, via embedding and strategic data duplication, is often encouraged for read performance. For example, embedding a product's name and price directly into an order item array within an order document, even if the full product details exist in a product's collection, means you can retrieve an entire order including item details with a single query, without needing to perform a join. The trade-off is that if the product's price changes, you'd need to update it not only in the product's collection, but also in any order item arrays where it's duplicated. This balance between read efficiency, fast, fewer queries, and write complexity, more updates, potential for stale data if not managed, is central to NoSQL schema design. Real-world scenarios and design patterns. User profiles. A user document can embed an array of addresses, phone numbers, or preferences, one to few, embedded. Blog posts and comments. Posts are in one collection. Comments could be in a separate collection, each referencing a posted, one-to-many, referenced. This allows comments to scale independently and avoids large, growing arrays within post documents. Product catalog. Products, categories, and tags. Products could embed an array of tags, and categories could embed an array of subcategories complex, often combined embedding referencing. Ultimately, MongoDB schema design is about understanding your application's access patterns. What data is accessed together? What data changes frequently? What are your most common queries? Design your schema to optimize for your most frequent read operations and embrace the document model's flexibility. The process is often iterative, allowing you to adapt your schema as your application evolves, a capability that sets MongoDB apart in the database world. In the next chapter, we'll see how to leverage these design decisions to further enhance performance through indexing. Chapter 6: Indexing for Performance, Speeding Up Your Queries. In the previous chapter, we delved into the crucial art of schema design in MongoDB, focusing on how to structure your data for flexibility and efficiency. While a well-designed schema is foundational, it's only half the battle when it comes to performance. The other equally critical component, especially as your datasets grow, is indexing. So, what exactly are indexes and why are they so crucial? Imagine you have a physical phone book containing thousands of names and phone numbers. If you want to find someone's number, you don't start reading from the very first page. Instead, you use the alphabetical index at the beginning to quickly jump to the right section. This is precisely what a database index does. It's a special data structure that stores a small portion of the data in an easily traversable form, typically sorted, that allows the database to quickly locate specific documents without having to scan every single document in a collection. Without indexes, MongoDB would have to perform a collection scan for most queries, meaning it would read every single document to find those that match your criteria. This is incredibly inefficient and slow for large collections. Creating and managing indexes. In MongoDB, you create an index using the createIndex method on a collection. You specify the field or fields to index and the order, one for ascending, for descending. For example, db.usersCreateIndex, email. One would create an ascending index on the email field in the user's collection. This index would make queries by email, like db.usersfind, email. John Doe at example.com, significantly faster. You can view the indexes on a collection using db.collectionGetIndexes, and you can drop an index using db.collectionDropIndex. Types of indexes. MongoDB supports several types of indexes, each optimized for different query patterns. Single field index, the most basic type created on a single field. For example, an index on userid. 1. Compound index, an index on multiple fields. This is incredibly powerful for supporting queries that filter or sort on several fields simultaneously. For example, db.productsCreateIndex, category. 1. Price, -1, would create a compound index that first sorts by category ascending, then by price descending. A query filtering by category and sorting by price could efficiently use this index. The order of fields in a compound index matters, as it affects which queries can use the index efficiently. Multi-key index, used for fields that hold arrays. If you index a field that contains an array, MongoDB creates a separate index entry for each element in the array. This allows for efficient querying within array elements. For example, if a tags field is an array, an index on tags would allow fast lookups for specific tags. Text index. As discussed in Chapter 4, these support text search queries on string content. You need to explicitly define a text index on the fields you want to search by keywords. Geospatial index, 2D sphere, 2D. Essential for performing location-based queries effectively. The 2D sphere index supports queries on Earth-like spheres, while 2D is for planar, flat geometries. Hashed index. Computes a hash of the field's value and indexes that hash. These are suitable for sharding using a hashed shard key, providing good distribution of data across shards. Covered queries, maximizing index efficiency. A query is considered covered by an index if all the fields in the query's filter and all the fields in its projection are included in the index. When a query is covered, MongoDB can answer the query solely using the index, without having to access the actual documents in the collection at all. This significantly reduces disk I/O and makes queries extremely fast. For example, if you have an index on name, 1 email, 1 in your user's collection, the query db.usersfind, name, John Doe, email, 1 id, 0 would likely be a covered query. MongoDB would find the name John Doe in the index, extract the associated email directly from the index entry, and never touch the full document. Partial indexes. Indexing a subset of data. Partial indexes allow you to index only those documents in a collection that satisfy a specified filter expression. This can lead to smaller indexes, lower storage requirements, and potentially better performance for certain workloads. For example, if you often query on documents that are active, you could create a partial index, db.usersCreateIndex, date joined, 1, partial filter expression, status, active. This index would only include documents where the status field is active. Unique indexes, ensuring data integrity. In addition to speeding up queries, indexes can enforce data constraints. A unique index ensures that no two documents in a collection have the same value for the indexed fields. For example, db.usersCreateIndex, email, 1, unique. True would prevent any two user documents from having the same email address. If you try to insert or update a document that violates this constraint, MongoDB will return an error. Monitoring index usage and performance. After creating indexes, it's vital to monitor their effectiveness. The explain method, as discussed in Chapter 4, is invaluable for this. It will show you whether your query used an index, which index it used, or if it resorted to a collection scan, COLLSCAN. You should aim to see IXSCAN index scan in your explain. Output for frequently accessed queries that you've indexed. MongoDB also provides a system profiler, dbset profiling level. That helps you track slow queries, giving you insights into which operations need index optimization. Atlas also offers robust monitoring tools to visualize index usage and query performance. Index best practices and common performance traps. Index your frequently queried fields. If you frequently query by userid, order date, or product SKU, these are prime candidates for indexing. Index on fields used in sort operations. Queries that filter and sort can benefit greatly from compound indexes where the sort fields are included in the index. Order fields in compound indexes. The equality, sort, range, ESR rule is a good guideline. Fields used for equality matches, EQ, should come first, then fields used for sorting, then fields used for range queries, GT, LT. Avoid over-indexing. While indexes speed up reads, they slow down writes, inserts, updates, deletes, because MongoDB has to update the indexes every time data changes. They also consume disk space. Create only the indexes you absolutely need. Index selectivity. Indexes are most effective on fields with high cardinality, many distinct values. Indexing a field that only has two possible values, like a Boolean isActive flag, will be less effective than indexing a userid field with millions of unique values. Understand your workload. Use explain and profiling to identify slow queries and then add indexes strategically. Don't add indexes speculatively. Avoid creating indexes on fields that will see frequent, arbitrary updates across many documents, as this can lead to write hotspots. Indexing is a powerful tool in your MongoDB performance toolkit. By strategically creating and managing indexes, you can dramatically improve the read performance of your applications, ensuring your users experience snappy response times even as your data grows to massive scales. The combination of thoughtful schema design and intelligent indexing is what truly unleashes MongoDB's capabilities. In the next chapter, we will explore another powerful feature for data analysis and transformation, the Aggregation Framework. Chapter 7, the Aggregation Framework, powerful data transformation. So far, we've learned how to insert, find, update, and delete individual documents, and how to query them with various operators and indexes for efficient retrieval. But what if you need to perform more complex data processing? What if you need to group documents, calculate sums or averages, restructure data, or join data from different collections? This is where MongoDB's Aggregation Framework takes center stage. The Aggregation Framework is a powerful tool designed for data transformation and analytics. It allows you to process data records and return computed results. Think of it like a multi-stage assembly line for your data. Documents enter the assembly line, pass through a series of stages, and are transformed, filtered, or combined at each step until the desired output is produced. This sequence of operations is called an aggregation pipeline. Each stage in an aggregation pipeline performs a specific data processing operation on the input documents and passes the resulting documents to the next stage. This sequential processing allows for highly flexible and powerful data manipulation. You typically start an aggregation pipeline using the aggregate method on a collection, providing an array of aggregation stages. Let's explore some of the most common and powerful stages. Match. Analogous to the find method, the match stage filters documents to pass only those that match the specified query criteria to the next stage. It's often the first stage in a pipeline, as it reduces the number of documents processed by subsequent stages, leading to better performance. For example, to only work with products that are in the electronics category. Match category, electronics, project. This stage reshapes each document in the stream. It can include, exclude, or rename fields or create new fields based on expressions. Similar to the projection in a find query, but more versatile. You can specify one to include a field, 0 to exclude it, or define new fields with complex expressions. For instance, to get only the name and price fields and create a new field discounted price. Project. Id, 0 name, 1 price, 1 discounted price. Multiply, price, 0.9. Group. This is one of the most powerful stages for data aggregation. It groups documents by a specified key and performs aggregate functions, called accumulators, on the group data. Common accumulators include sum, AVG, min, max, and count, to calculate the total number of products in each category. Group. Id. Category, total products. Sum, 1. Here, id specifies the grouping key, the category field, and sum, 1 counts each document in the group, to get the average price per category. Group. Id. Category, average price. AVG, price. Sort sorts the documents in the stream. Works exactly like the sort method we discussed in Chapter 4, taking a document with field order pairs, one for ascending, for descending. Often used before limit or at the end to order the final results. Limit limits the number of documents passed to the next stage, useful for getting the top n results after sorting. Skip skips a specified number of documents, similar to the skip method in queries. Useful for pagination within an aggregation pipeline. Data transformation, unwind, and lookup. Beyond basic aggregation, the framework provides stages for more complex data transformation. Unwind. This stage deconstructs an array field from the input documents to output a document for each element. For example, if a document has an array of tags. Electronics, mobile. Unwind on the tags field would produce 2 documents, one for electronics and one for mobile, each with the original document's other fields. This is invaluable when you need to process individual elements within an array. Lookup, left outer join. This is MongoDB's equivalent of a left outer join from relational databases. It allows you to perform a join operation on unsharded collections in the same database. You can combine data from 2 collections based on a common field. For example, if you have an orders collection with a customer id and a customers collection with id and name, you could use lookup to add customer details to each order. DB orders aggregate. Lookup. From customers, the collection to join. Local field, customer id, field from the input documents orders. Foreign field, id, field from the from collection customers. As customer details, the name of the new array field to add to the input documents. This would add an array named customer details to each order document, containing information about the matching customer. If the customer ID is unique, this array typically contains one element. This allows you to combine and denormalize data on the fly within the pipeline, combining stages for complex analytics. The real power of the aggregation framework comes from combining these stages sequentially. Each stage refines the data, passing a potentially new set of documents to the next. Practical example: monthly sales report. Let's say you have an orders collection and you want to generate a monthly sales report showing total sales and the average item price for each month. Documents like ID, order date, ISO date, 2023 to 1 to 15 T1000Z, total amount, 150.00 items, price, 50, price, 100, DB orders aggregate. Stage 1, filter to a specific year, optional for performance. Match, order date, GT, ISO date, 2023 to 1 to 0, 1 T000Z, LT. ISO date, 2024 to 1 to 0, 1 T000Z. Stage 2, group by month, calculate total sales and average item price for each month. Group, ID, date to string, format, %y%m, date, order date, group by year month string. Total sales, sum, total amount. AVG item price, AVG. AVG, items price. Calculate AVG of item prices within each order, then AVG of those AVGs. Order count, sum, 1. Stage 3, project to rename ID field and optionally reshape output. Project, ID, 0, exclude the default ID. Month ID, rename ID to month. Total sales, 1. AVG item price, 1. Order count, 1. Stage 4, sort by month. Sort month 1. This pipeline first matches orders from 2023, then groups them by month using a date formatting operator, calculating sums and averages. It then reshapes the output to be more readable and finally sorts the results chronologically. This demonstrates how multiple stages can build upon each other to produce complex analytical results. Performance considerations for aggregation pipelines. Match early. Always try to put match stages as early as possible in your pipeline. This filters the document stream, reducing the number of documents that need to be processed by subsequent, potentially more expensive stages. Indexes, match and sort stages can effectively use indexes to speed up the pipeline. Ensure you have appropriate indexes on the fields used in these stages. Memory limits. Aggregation pipelines have a default memory limit, 100 MB. If a stage exceeds this, it may write data to temporary files on disk, which can slow down performance or fail entirely. For larger operations, you might need to allow disk use, true, or scale your MongoDB server. Pushdown optimization. MongoDB can often optimize stages by pushing down operations. For example, if a project stage follows a match that uses an index, MongoDB might apply the projection as data is read from the index. The aggregation framework is an incredibly powerful feature that allows you to perform sophisticated data analytics and transformations directly within MongoDB. It's an indispensable tool for generating reports, building ad hoc queries, and preparing data for display in dashboards or further analysis. Understanding and mastering its stages will significantly expand your capabilities as a MongoDB developer. In our next chapter, we will discuss replica sets, the foundation for ensuring high availability and read scalability for your MongoDB deployments. Chapter 8, Data Replication, ensuring availability and read scalability. Up to this point, we focused on interacting with a single MongoDB instance. While perfectly fine for development and small projects, a single server presents a critical vulnerability. What happens if that server goes down? All your data becomes inaccessible and your application grinds to a halt. This is where data replication comes into play. In the landscape of production-grade applications, ensuring high availability and data redundancy is paramount. High availability means your system remains operational even if some components fail. Data redundancy means having multiple copies of your data, so the loss of one copy doesn't mean data loss. In MongoDB, these crucial needs are addressed through replica sets. A replica set is a group of MongoDB processes that maintain the same data set. It provides redundancy and high availability. At its simplest, a replica set consists of a primary member and one or more secondary members. The primary member is the only member in the replica set that receives all write operations. Think of it as the current leader or the active database server that handles all changes. Secondary members replicate the data from the primary member. They maintain an identical copy of the data and can be used for read operations, thereby distributing the read load. If the primary member fails, secondaries are crucial for recovery, as one of them can be elected as the new primary. The process of replication in MongoDB works as follows. The primary records all its data changes, write operations, like inserts, updates, and deletes, in a special capped collection called the oplog operation log. Secondary members then continuously copy and apply these operations from the primary's oplog to their own datasets, ensuring they stay synchronized. One special type of member called an arbiter can also be part of a replica set. An arbiter does not store any data. Its sole purpose is to participate in elections to determine which member should become the new primary if the current primary becomes unavailable. Arbiters are lightweight and consume minimal resources, making them useful in situations where you need to break ties in an odd number of voting members without dedicating a full data-bearing server. For example, a 3-member replica set could consist of 2 data-bearing members, primary, secondary, and 1 arbiter. The most critical feature of a replica set is its ability to perform automatic failover. If the primary member becomes unreachable due to hardware failure, network outage, or planned maintenance, the remaining secondary members automatically hold an election to choose a new primary from among themselves. This process typically takes only a few seconds, minimizing downtime for your application. Your application generally doesn't need to manually detect this. The MongoDB driver, the library your application uses to connect to MongoDB, handles detecting the new primary. Read preferences, directing traffic to members. While the primary handles all writes, you have flexibility in how your application directs read operations using read preferences. Primary. This is the default. All read operations go to the primary. This ensures the strongest consistency. You always read the most up-to-date data. Primary preferred. Reads typically go to the primary, but if the primary is unavailable, the read is directed to a secondary. This balances consistency with availability. Secondary. Reads go to any available secondary member. This is excellent for read scalability, as you can add more secondary members to handle increasing read load. However, there might be a slight replication lag, meaning the data you read from a secondary might be slightly out of date compared to the primary. Secondary preferred. Reads typically go to secondaries, but if no secondaries are available, reads are directed to the primary. Nearest. Reads are directed to the member, primary or secondary, with the lowest network latency to the client. This is good for geographically distributed applications where you want the fastest response time. Choosing the right read preference depends on your application's consistency requirements and read load patterns. Write concerns. Ensuring data durability. Just as read preferences control where reads go, write concerns determine the level of acknowledgement MongoDB requires for a write operation to be considered successful. This directly impacts data durability and consistency. W1 default acknowledges write once the primary has applied the operation. W0 fire and forget, no acknowledgement is requested from MongoDB. Fastest but no guarantee of delivery or success. Not recommended for critical data. W majority acknowledges write once the primary and a majority of the voting members in the replica set have applied the operation. This offers a very strong guarantee of durability, as the data is persisted across multiple independent members before the client receives confirmation. This is often recommended for critical write operations. W number acknowledges write once the primary and specified number of other members have applied the operation. Setting up a replica set. Conceptual overview. While the exact commands can be found in the official documentation, conceptually, setting up a replica set involves starting multiple MongoDB instances, each on a different port or server. Ensuring each instance is aware that it's part of a replica set by specifying a REPL set name in its configuration or command line. Connecting to one of the MongoDB instances, typically the one intended to be primary. Initiating the replica set using rs.initiate. This command takes a configuration object detailing all the members of the set. Adding secondary members using rsadd, hostname, port. Monitoring the status of the replica set using rsstatus in the Mongosh shell. This command provides a detailed report on the health, roles, and replication lag of all members. Failure scenarios and automatic failover. Consider a replica set with a primary P and two secondaries S1, S2. If P goes down, S1 and S2 detect the outage. They hold an election. If S1 wins, it becomes the new primary. S2 then replicates from S1. If S1 goes down, no election occurs. P continues as primary, S2 continues replicating from P. The automatic failover mechanism makes replica sets robust against single-point failures, making them an essential component for any production-ready MongoDB deployment. In summary, replica sets are the cornerstone of high availability and data redundancy in MongoDB. They provide automated failover, distribute read load across multiple servers, and allow you to configure data durability based on your application's needs. By architecting your MongoDB deployment with replica sets, you ensure that your data is safe and your application remains accessible to users. While replica sets provide redundancy for failure and some red scalability, for truly massive datasets and write throughput, you'll need to look at sharding, which we'll explore in the next chapter. Chapter 9, Sharding, Scaling Out Your Database Horizontally. In the journey so far, we've learned how to design our data, query it efficiently, and ensure its availability and consistency using replica sets. Replica sets are excellent for providing redundancy and handling increased read traffic by distributing reads across multiple secondary nodes. However, even with replica sets, your overall write throughput is still ultimately limited by the capacity of a single primary node, and the entire dataset must fit on that primary node's storage. For truly massive datasets that exceed the capacity of a single server, or for applications that require extremely high write throughput across geographically dispersed users, we need to employ a more advanced scaling strategy. Sharding. The need for sharding arises when a single replica set can no longer cope with the demands of your application. This could be due to data volume. Your dataset grows too large to fit on a single server's disk or memory. Write throughput. The write operations overwhelm the primary node, leading to bottlenecks. Geographic distribution. You want to place data closer to users in different regions to reduce latency. Sharding is MongoDB's method for scaling out your database horizontally. It's the process of distributing large datasets across multiple independent MongoDB instances, called shards. Each shard is a replica set itself, providing both redundancy and scalability for a portion of the data. A sharded cluster in MongoDB is composed of several key components. Shards, these are the actual data-bearing nodes. Each shard is a replica set, ensuring high availability and redundancy for the data it holds. When data is sharded, it's divided into logical chunks, and each chunk is stored on a specific shard. Config servers. These store the cluster's metadata, including which chunks of data reside on which shard, and information about the shard key ranges. Think of them as the brain of the cluster, maintaining its organizational map. For high availability, config servers are deployed as a replica set, a config server replica set. Mongo's routers. These are query routers. Your application connects to a Mongo's instance, not directly to a shard. The Mongo's acts as a proxy, routing client requests to the appropriate shards. It knows where each piece of data lives by querying the config servers. For a client, interacting with a sharded cluster through Mongo's feels much like interacting with a single MongoDB instance. The most critical design decision in a sharded cluster is choosing a shard key. This is the field or fields within your documents that MongoDB uses to determine how to distribute data across the shards. The shard key is immutable for a document after its creation, and a good shard key design is paramount for an efficient and scalable sharded cluster. Shard key types and considerations. Range-based sharding. Documents are distributed based on ranges of the shard key values. For example, if you shard on a zip code field, documents with zip codes from 0 to 10,000 go to shard A, 10,001 to 20,000 to shard B, and so on. Pros: efficient for range queries, e.g., find all users in zip codes between 10,000 and 20,000. Cons: can lead to uneven data distribution or hotspots if data growth or query patterns are concentrated in specific ranges, e.g., if most of your users are from New York, all New York data goes to one shard. This is especially a concern for monotonically increasing keys like timestamps or auto-incrementing IDs, where new writes would consistently go to the same shard. Hashed sharding. Documents are distributed based on a hash of the shard key value. MongoDB computes a hash of the shard key and uses this hash value for distribution. Pros: provides a more even distribution of data across shards, reducing the chance of hotspots, especially for keys that would otherwise be monotonically increasing. Excellent for equal distribution of write load. Cons: range-based queries on the shard key are less efficient because the hashed values no longer preserve the original order. If your most common queries involve ranges on the shard key, a hashed shard key might not be optimal. A good shard key strives for two main goals: even distribution of data. Data should ideally be spread evenly across all shards to prevent any single shard from getting overloaded. Even distribution of write operations. Write operations should also be distributed evenly across shards to prevent write hotspots. Support for common queries. Queries that include the shard key in their filter can be routed directly to the specific shards that contain the relevant data, making them highly efficient, targeted queries. Balancers and chunks. How data is distributed and managed. MongoDB automatically manages data distribution within a sharded cluster using two concepts. Chunks. Data within a sharded collection is divided into contiguous ranges of the shard key, called chunks. By default, chunks are 64 megabytes in size. Balancer. A process that runs in the background to ensure that chunks are evenly distributed across the shards. If one shard has significantly more chunks than others, the balancer automatically migrates chunks from overloaded shards to underloaded ones. This happens transparently to the application. Setting up a sharded cluster, conceptual overview. Similar to replica sets, setting up a sharded cluster involves several steps. Deploy config servers. Start a replica set of MongoDB instances configured as config servers. Deploy shards. Start multiple MongoDB instances, each configured as a replica set that will act as your shards. Start Mongo's routers. Launch one or more Mongo's instances that your application will connect to. Add shards to the cluster. Use shadd shard from a Mongo's shell to tell the Mongos and config servers about your replica set shards. Enable sharding for a database. Use enable sharding my database. Shard a collection. Use shard collection, my database my collection, shard key, one or hashed, to define the shard key and begin data distribution for a specific collection. Common sharding pitfalls and best practices. Poor shard key choice. This is the most damaging mistake. A bad shard key leads to inefficient routing, hotspots, and defeats the purpose of sharding. Invest significant time in designing your shard key. Cardinality. The shard key should have high cardinality, many unique values, to ensure an even distribution of data. Frequency. The shard key should be frequently accessed in your queries to allow for targeted query routing. No changing shard keys. Once a collection is sharded, its shard key cannot be changed. If you need a different shard key, you'll have to migrate your data to a new collection with the new key. Read-write patterns. Understand how your application reads and writes data and design the shard key to support those patterns effectively. Pre-splitting chunks. For very large, growing datasets, or if you anticipate a massive influx of data, you can pre-split chunks before inserting data to help distribute writes more evenly from the start. Sharding is a powerful, yet complex, topic in MongoDB. It allows you to scale your database horizontally to handle virtually limitless data volumes and write throughput. It's a foundational component for building applications that operate at immense scale. And while it adds architectural complexity, it provides the necessary infrastructure to grow beyond the limits of a single server. In the next chapter, we will shift our focus to an equally critical aspect of production deployments: security. Chapter 10: Security Best Practices for Developers. Throughout this book, we've covered how to design, query, scale, and manage your MongoDB data effectively. However, none of these capabilities matter if your data isn't secure. In today's digital landscape, data breaches are rampant, and the consequences can be severe, ranging from financial penalties and reputational damage to complete business failure. For developers, understanding and implementing robust security measures is not an afterthought, but a core responsibility. The importance of database security cannot be overstated. Your database typically holds your most sensitive assets: user data, financial records, personal identifiable information, PII, and intellectual property. Protecting this data from unauthorized access, modification, or destruction is paramount. MongoDB, like any powerful database, provides a comprehensive suite of security features, but it's up to you to configure and use them correctly. Let's break down the key security components and best practices for MongoDB. First and foremost is authentication. This is the process of verifying a user's identity. By default, MongoDB might allow connections without authentication, which is acceptable for isolated development environments, but absolutely unacceptable for production. You must enable authentication on your MongoDB server. Once enabled, users trying to connect to the database must provide a valid username and password. Along with authentication comes authorization, which is about controlling what an authenticated user can do. MongoDB implements authorization through role-based access control, RBAC. Instead of assigning individual permissions to users, you create roles, assign privileges, specific actions on specific resources to those roles, and then grant roles to users. For example, you might create a read-only user role that grants permissions to find, read documents in specific collections, and an app user role that grants find, insert, update, and delete permissions on application collections. Then, you create users and grant them these predefined roles. This approach simplifies management and improves security, as you can easily audit what each role is permitted to do. MongoDB comes with many built-in roles: read, read-write, DB admin, cluster admin, etc. But you can also create custom roles tailored to your application's precise needs. Encryption is a critical layer for protecting data. There are two main types to consider. Encryption at rest. This secures your data when it's stored on disk. This is typically achieved by using a file system level encryption, like LUKS on Linux, BitLocker on Windows, or a full disk encryption solution. For MongoDB Enterprise Advanced, there's also native Wired Tiger Storage Engine encryption, which encrypts data files and journal files directly. This protects your data even if someone gains physical access to your server's storage media. Encryption in transit, TLS SSL. This secures the communication channel between your MongoDB clients, your application, Mongosh, Compass, and the MongoDB server. You should always enable TLS SSL, formerly SSL, for all connections, especially in production environments or over untrusted networks. This prevents eavesdropping and tampering with data as it travels across the network. If your connection string to Atlas starts with MongoDB plus SRV, // it indicates an encrypted connection is being used, which is excellent. Auditing database activity is crucial for security compliance and incident response. MongoDB Enterprise offers a native auditing feature that allows you to record specific operations performed against your database, including who performed them, when, and from where. This creates a forensic trail that can be invaluable for detecting suspicious activity, investigating incidents, and proving compliance. Network security forms the perimeter defense around your database. Firewalls. Configure firewalls to restrict network access to your MongoDB instances. Only allow connections from trusted application servers, jump hosts, or specific IP ranges. Never expose your MongoDB port, default 27017, directly to the public internet unless absolutely necessary and with extreme care. IP whitelisting. If you're using MongoDB Atlas, explicitly whitelist the IP addresses or network ranges that are allowed to connect to your cluster. This provides an additional layer of protection, preventing connections from unauthorized locations. Virtual private clouds, VPCs/private endpoints. For cloud deployments, configure your instances to be within a virtual private cloud, VPC, and use private endpoints or VPC peering to connect your application servers directly to your MongoDB instances over a private, secure network, bypassing the public internet entirely. Protecting sensitive data requires a multifaceted approach. Data masking redaction. For non-production environments, development, staging, consider masking or redacting sensitive production data. Never use real personal data for development or testing if it can be avoided. Application-level security. Not all security can happen at the database level. Your application code needs to implement secure coding practices, e.g., input validation, parameterization to prevent injection attacks, secure session management. Hashing passwords. Never store user passwords in plain text. Always hash them using a strong, industry-standard hashing algorithm like bcrypt before storing them in the database. Principle of least privilege. Grant users and applications only the minimum necessary privileges to perform their functions. Do not give an application full DB admin access if it only needs to read and write to specific collections. This limits the blast radius in case a credential is compromised. Common security vulnerabilities and how to prevent them. Unauthenticated access, the most common and catastrophic mistake. Always enable authentication. Weak passwords. Use strong, unique passwords for all database users. Consider using a password manager. Insecure network exposure. Exposing MongoDB directly to the internet without proper firewall rules. Always restrict access to trusted sources only. Default settings. Failing to change default usernames, passwords, or configurations. Outdated software. Running old versions of MongoDB that have known security vulnerabilities. Regularly update your MongoDB instances to the latest stable versions. Lack of encryption. Not encrypting data in transit or at rest. In essence, securing your MongoDB deployment requires a holistic approach that covers authentication, authorization, network security, encryption, and continuous monitoring. As a developer, integrating these security considerations into your application's design and deployment lifecycle from the very beginning is critical. Ignoring security is not just irresponsible. It can be devastating. With a solid understanding of these best practices, you can build applications on MongoDB with confidence, knowing your data is well protected. Our next chapter will focus on application integration, bridging the gap between your application code and your secure MongoDB instance. Chapter 11, Application Integration, Connecting Your Code to MongoDB. So far, we've explored MongoDB's architecture, its data model, querying capabilities, performance optimizations, and critical security considerations. But a database is only truly useful when your applications can interact with it seamlessly. This chapter bridges the gap between your conceptual understanding of MongoDB and its practical application by demonstrating how to connect your code and perform operations. At the heart of connecting applications to MongoDB are the official MongoDB drivers. These are client libraries developed and maintained by MongoDB Inc. and the community for various programming languages. The beauty of these drivers is that they provide a consistent, idiomatic API for interacting with MongoDB, meaning that while the syntax might vary slightly between languages, the underlying concepts and methods map directly to the database operations we've discussed. Whether you're writing an application in Node.js, Python, Java, C#, or Go, you'll find a well-supported driver that handles the complexities of network communication, BSON serialization, connection pooling, and error handling. Let's look at the general patterns for connecting from popular languages. While we won't show full code blocks, as they don't translate well to audiobooks, we'll describe the steps and concepts common to most official drivers. Installation. The first step is to install the appropriate MongoDB driver for your language using its package manager, e.g., npm for Node.js, pip for Python, maven/gradle for Java, NuGet for C#. You would search for MongoDB driver language name or similar. Importing the driver. In your application code, you'll import the necessary classes or modules from the installed driver. Establishing a connection. This is typically done by creating a Mongo client or similar object and providing a connection string. The connection string is a URI-like format that specifies the hosts, ports, database name, authentication credentials, and various other connection options. For a local instance on default port, MongoDB //localhost:27017. For a replica set, MongoDB //host1 port 1 host 2, port 2/ replica set equals my replica set. For MongoDB Atlas, the string will be much longer, starting with MongoDB plus srv // automatically configuring TLS SSL and connecting to the appropriate cluster members. Once you have the connection string, you'll call a connect method, which establishes the connection to your MongoDB server. This operation typically returns a promise or requires a callback function, as database connections are asynchronous. Selecting a database and collection. Once connected, you get a reference to the client object. From this, you can select a specific database using clientDB, your database name. From the database object, you then select a collection, db.collection, your collection name. Performing operations. The collection object provides methods that directly map to the CRUD operations we've covered. Insert one, find, update one, delete many, etc. The arguments to these methods are typically JavaScript-like objects, dictionaries in Python, maps in Java that represent your query filters, update documents, or projection specifications. Handling connections and connection pooling. Creating a new connection for every database operation is inefficient and can quickly exhaust server resources. Therefore, MongoDB drivers implement connection pooling. When you call client.connect, the driver typically establishes a pool of connections that can be reused by multiple requests from your application. This dramatically improves performance. As a developer, the best practice is to establish a single Mongo client instance at the start of your application and reuse it throughout your application's lifecycle. Only close the connection when your application is shutting down. Error handling and retry logic. Database operations are inherently susceptible to network issues, server failures, or invalid data. Robust applications must include proper error handling. Drivers typically throw exceptions or return error objects when an operation fails. Your code should catch these errors and handle them gracefully, perhaps by logging the error, informing the user, or implementing retry logic for transient network issues. For example, if a write operation fails due to a network blip, you might implement an exponential backoff strategy to retry the operation a few times. Transactions in MongoDB, starting and committing. While MongoDB's document model encourages embedding to avoid multi-document transactions, sometimes your application requires the ACID guarantees of a transaction across multiple documents or even multiple collections. Since MongoDB 4.0, multi-document transactions have been supported across replica sets, and since MongoDB 4.2, they are supported across sharded clusters. Using transactions involves starting a session. You first need to create a client session. Starting a transaction, call start transaction on the session. Performing operations, execute your read and write operations within the transaction, e.g., session with transaction. Committing or aborting. If all operations succeed, you commit transaction. If any fail, you abort transaction, which rolls back all changes made within that transaction. This ensures that a series of operations are either all completed successfully or all rolled back, maintaining data integrity. It's important to note that transactions have performance overhead, so use them judiciously only when strict ACID guarantees are required across multiple documents. Object Document Mappers, ODMs, / Object Relational Mappers, ORMs. For many developers, interacting directly with driver methods and raw JSON-like objects can become cumbersome, especially in complex applications. This led to the development of ODMs, Object Document Mappers, for NoSQL databases, conceptually similar to ORMs for relational databases. An ODM provides a higher-level abstraction layer, allowing you to work with your database as if you were working with native programming language objects. For example, in Node.js, Mongoose is a very popular ODM. With Mongoose, you define schemas, not to be confused with MongoDB's flexible schema sense, but more like application-level data models that map to your MongoDB collections. You can then create, read, update, and delete objects using familiar object-oriented paradigms. And Mongoose handles the translation to and from MongoDB's BSON format, validation, and even query building. While ODMs can boost productivity by providing model definitions, validation, and middleware, they sometimes abstract away too much, potentially making it harder to leverage MongoDB's specific features or optimize complex queries. It's a trade-off between convenience and granular control. Many developers start with an ODM for rapid development and then drop down to the native driver for performance-critical or highly specific operations. Building a simple web application with MongoDB conceptual walkthrough. Imagine a web application that stores user profiles. Backend framework. You'd choose a web framework, e.g., Express.js for Node.js, Flask/Django for Python, Spring Boot for Java. Database connection. On your application startup, or within a configuration module, you would establish the single, long-lived Mongo client connection. API endpoints. You define API endpoints, e.g., users, id. A post-users endpoint would receive user data from the client. Your application logic would validate this data and then use db.users.insert1 user data to save it to MongoDB. A GET users endpoint would call db.usersFind to array to retrieve all users with pagination and filtering, of course, in a real app and send them back to the client. A GET/users/id endpoint would use db.users, find one, id, new object ID, d, to fetch a specific user. Note, the id received from a URL parameter is usually a string and needs to be converted to MongoDB's object-id type for querying. Put/delete endpoints would similarly map to update1/delete1. Error handling and response. Your application would wrap these database calls in try-catch blocks or use promise.catch to handle potential database errors and send appropriate HTTP error responses to the client. Effective application integration is where all the theoretical and practical knowledge of MongoDB comes together. By leveraging the official drivers, understanding connection management, and applying proper error handling, you can build robust, high-performing applications that harness the full power of your MongoDB database. Finally, in our concluding chapter, we will discuss performance tuning and monitoring, ensuring your integrated applications continue to run smoothly and efficiently. Chapter 12. Performance tuning and monitoring tips. You've designed your data, secured your database, scaled it with replica sets and sharding, and integrated it seamlessly with your applications. But the journey doesn't end there. As your application grows, traffic increases, and data Arabic het Arabic Jim Arabic meme expands, you'll inevitably encounter performance challenges. This final core chapter is dedicated to the art and science of performance tuning and monitoring in MongoDB, equipping you with the knowledge to diagnose, optimize, and maintain a high-performing database system. Performance tuning begins with understanding where bottlenecks typically occur. For a database system like MongoDB, these usually fall into four main categories. CPU. Is the server's processor maxed out, struggling to handle queries or internal operations? Memory, RAM. Is the database constantly swapping data to disk because it doesn't have enough RAM to hold frequently accessed data or indexes? Disk I/O. Is the system spending too much time reading from or writing to storage, indicating slow disks or inefficient data access patterns? Network. Are there latency or throughput issues between your application servers and the database, or within your replica set sharded cluster? Identifying these bottlenecks requires proper monitoring. MongoDB provides several built-in tools and mechanisms, and there are external solutions as well. Mongostat, a command line utility that provides a quick overview of the current status of a Mongo instance. It reports various metrics, including insertions, queries, updates, deletes, dirty data percentage, and resident memory usage. It's great for real-time, high-level snapshots. MongoTop. This utility tracks and reports the current read and write activity of a MongoDB instance on a per-collection basis. It shows you which collections are most active, helping you identify hot collections that might require specific optimization or careful shard key selection. MongoDB Atlas Monitoring and Performance Advisor. If you're using MongoDB Atlas, you get a rich, intuitive dashboard with comprehensive metrics: CPU, RAM, disk I/O, network, query execution times, replication lag, etc. Atlas's Performance Advisor can automatically suggest indexes, highlight slow queries, and identify security vulnerabilities. This is often the easiest way to get deep insights into your cluster's health. Server Status Command. In the Mongosh shell, DB Server Status provides a wealth of information about the current state of the database, including memory, connections, network I/O, background flushing, and operation counters. It's a verbose output, but invaluable for detailed analysis. Beyond real-time metrics, the MongoDB logs are your essential tool for troubleshooting and gaining deeper insights. MongoDB logs a wide range of events, including slow queries, connection attempts, replication status changes, and errors. By default, queries exceeding 100 milliseconds are logged as slow queries. By analyzing these logs, you can identify specific queries that are performing poorly and then use explain to understand why. Logs also provide information on index builds, disk errors, and configuration changes, all of which are crucial for maintaining a healthy and performant database. Best practices for application-side performance. While much of performance tuning focuses on the database server, your application code plays a crucial role. Connection pooling. As discussed in Chapter 11, always use connection pooling. Establish one Mongo client instance and reuse it throughout your application. Index awareness. Design your queries to leverage indexes. Before writing a query, consider what indexes could accelerate it. Use explain during development to confirm your queries are using indexes as expected. Limit and project. Always use limit to restrict the number of results returned, especially for user-facing lists. Use project to retrieve only the necessary fields, reducing data transfer and memory consumption. Batch operations. Whenever possible, use insert many, update many, and delete many, instead of individual insert one, update one, delete one calls. This significantly reduces network round trips. Write concerns. Choose appropriate write concerns. For non-critical data, a lower write concern may improve write throughput at the cost of durability guarantee. For critical data, use W. Majority. Read preferences. Direct reads to secondaries where appropriate, secondary preferred, secondary, especially for queries that can tolerate slight replication lag, to offload the primary. Avoid or and regular expressions without indexes. While powerful, queries using or operator on unindexed fields or regular expressions that don't start with an anchor can trigger collection scans. Optimal schema design. Revisit Chapter 5. An effective schema, embedding versus referencing, aligned with your application's access patterns, remains foundational for performance. Hardware and infrastructure considerations. The underlying hardware and infrastructure directly impact MongoDB's performance. RAM. This is often the most critical resource. More RAM allows MongoDB to hold more of your data and indexes in memory, the resident set size, reducing reliance on slower disk I/O. Aim for your working set, frequently accessed data and indexes to fit in RAM. SSDs, solid-state drives. For I/O-bound workloads, SSDs are essential. Their faster random I/O performance massively outperforms traditional. CPU. Multi-core CPUs are beneficial, as MongoDB can leverage multiple cores for many operations. Network. Ensure low latency, high bandwidth connections between your application servers and database nodes, and within your replica set sharded cluster. Cloud provider choices. Consider the performance tiers offered by cloud providers. Dedicated instances often provide more consistent performance than burstable or shared resources. Capacity planning and scaling strategies. Performance tuning is also about planning for future growth. Monitor trends. Continuously monitor resource usage to identify trends and predict when you'll hit capacity limits. Vertical scaling. Upgrade hardware, more RAM, faster CPU, larger SSDs. This is often the first step, but eventually you'll hit limits. Horizontal scaling. Beef up replica sets, add more secondaries to handle increasing read load. Sharding. When a single replica set becomes a bottleneck for writes or data capacity, implement sharding to distribute data and load across many servers. Common performance tuning scenarios. Slow queries, diagnosis. Use explain and DB set profiling level 1, SLOMs, 100 to identify the specific queries and why they're slow, often COLLSCAN. Solution, add appropriate indexes. Refactor query to use existing indexes more effectively. High CPU usage, diagnosis. Examine MongoStat, server status, and profiler logs. Are there many complex aggregations? Unindexed queries? Solution, optimize queries, ensure indexes are used, refine aggregation pipelines, scale vertically, or consider sharding to distribute compute. High disk I/O, diagnosis. Check MongoStat and server status, metrics, flush-ups, page faults total. Is the working set larger than RAM? Solution, add more RAM, use faster SSDs, optimize indexes, making them more precise or partially indexed. Avoid full collection scans. Network latency, diagnosis. Ping from application server to database. Check network configuration. Solution, collocate application and database servers in the same region availability zone. Use private networking within cloud environments. Write hotspots, specific to sharding. Diagnosis, identify an uneven distribution of writes or data using MongoTop or Atlas monitoring for sharded clusters. Solution, this typically means a poor shard key choice. Reevaluate your shard key. Potentially reshard using a different key like a hashed shard key if writes are concentrated. Performance tuning is an ongoing process, not a one-time fix. By consistently monitoring your MongoDB deployment, understanding its logs, and applying the best practices learned throughout this book, you can ensure your applications remain fast, responsive, and scalable as they grow. This concludes our technical deep dive into MongoDB for developers. In our final section, we'll reflect on your journey and point you towards continuous learning resources.